electrodynamics. Again, we are going to calculate the magnetic field due to a long wire. But hold on, because there's a whole bunch of awesome stuff here. Number one, we're going to do it by first calculating the magnetic vector potential. And you may say, this is dumb. But trust me, at one point in your career, you're going to say, that magnetic potential, vector potential, kind of cool. So what I'm going to do, long rod, not infinite, long rod, calculate the vector potential, use that to calculate the magnetic field. The magnetic field is the curl of the magnetic potential. Now, there's a bunch of stuff here because I'm going to do magnetic vector potential. Then I'm going to plot the magnetic vector potential. Then I'm going to calculate the magnetic field, and then I'm going to numerically calculate the magnetic field. There's so much stuff here. And if you wait till the whole video, I'm going to give you a double high five. I might forget, and if I do forget to give you a double high five, then just let me know, and I'll send one to you. A double high five. Okay. So long rod, length L, current I in the z-axis. We're going to find the magnetic field on the at the x location. So the first thing, let's just talk about this magnetic vector potential. Basically, this comes from number one, Ampere's law says that del cross B is mu naught J, where J is the current density. And if you put that in, and if you put this into B right there, and you assume del dot A is 0, which we can pick, it's possible, it's our choice, then you get this. And I've already went over this in other videos, so I'm not going over all the details. Del squared Laplacian of A is negative mu naught J, and that looks just like the Poisson's equation for electric potential, and so we can use a similar form for the vector potential that we did for electric potential. So then, and even though it's a vector, it all works. So I'm going to skip all the steps. We know that A is mu naught over 4 pi, the integral over all space, J dV over R. That's important. So I'm going to put a box around it, even though I'm going to erase it in just a second. Okay, so we can calculate the vector potential by breaking this into infinitely number of pieces and then just add them up. That's what that says, where the current density J is the current per unit area. Now, this works if we choose this. So there's a lot of weird things about the vector potential. Number one, it has no physical thing that you can say, oh, it's this. The electric potential, the scalar electric potential, you can say, well, that's like the change in energy per unit charge. So you don't have that here, but it's still useful. Okay, get into it. We already did this, remember, so we can check our answer. But let's just get started. So here we have mu naught over 4 pi, cool. J, we need to get J. Actually, we need J dV because we have a really skinny wire. We don't really need to worry about how J changes over the volume. And then we need to calculate R. So let's do R first. So imagine that I have a little piece of this wire and has a length of dz. Now, I need to know the location of that piece, so let's call that the vector r, I. And then I need the vector location of where I want to find the vector potential, call that RO. And then this is R. So let's write down expressions for those. RO is just going to be, in this case, x, 0, 0. It's on the x-axis. Ri is on the z-axis. I was going to write z. So it's 0, 0, z. R is going to be RO minus R, I. So it's going to be x, 0, negative z. Now I'm going to need the magnitude of R. Well, that's pretty easy. Square root x squared plus z squared. Great. Okay, what do we need next? We need that J dV. Imagine that I had my wire is square. And it's really thin, it doesn't really matter. And so if I take a little piece of that, the volume element, dV, it's going to be dx, dy, dz. So dV is dx, dy, dz. And J, the current density, because I know the direction is in the z-hat direction, it's going to be I over a z hat. But we want to write that as a differential, so we're really talking about dA, because we have a really tiny area. So dA, I'll put that dA is dx dy, right? Because that gives me my area of this thing. So j dv is going to be j I z hat over dx dy, dx dy dz. Cancel, 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 cancel. So j is I dz z hat. Okay, we are ready to start plugging into our equation. Let's put some of these things over here just so we'll remember them. J equals j dv is I dz z hat, and then r is the square root of x squared plus z squared. We wouldn't really forget that. They're pretty easy to remember, so that's fine. But this just gives us more working room. So now I can write down the integral for a, mu naught over 4 pi. The integral from z is negative L over 2 to L over 2, right? The length of the whole thing is L, so down here I'm at negative L over 2. And then I have I'll put the I out here, dz 0, 0, 1, right? That's my z hat as a vector, divided by the square root of x squared plus z squared. So we need to integrate that. But we actually have 3 integrals, right? Because I have 3 components of the vector up there, and I have a vector over here. So I can say the x component of a is the integral where I use the x component of z hat, which is 0. So ax is 0. For the y component, I use the y component of z hat, which is 0. So ay is 0. So my only component is in the z direction. For a, because then if you're thinking what I just thought, I was like, wait, just double checking. That's wrong, because it's magnetic field. We're not calculating the magnetic field, we're calculating the vector potential. Okay, so now we can write our expression for az, mu naught I over 4 pi, the integral of dz over the square root of x squared plus z squared. Now, that's actually not a trivial integral, so I just am going to look it up in my handy dandy. You know, this course, how many times have I looked up integrals? It's usually the same one, but this one's actually different. I bookmarked this one because I knew I'd forget it. So we're under forms containing square root of x squared plus a squared right there. You can't see it. Okay. So, and if you look, number 157, let's see if you can see that. 157. That's exactly what we want. Okay. So this says that my answer is mu naught over 4 pi natural log of z plus the square root of x squared plus z squared from negative L over 2 to L over 2. Is that what it says? Yep, got it. I can put my bookmark back there because I might need that again. Okay, there's my book. So when we evaluate the limits, we're going to get a little messy. It's not a big deal. When we evaluate them, I really need a new piece of chalk. But I'm going to carry on. When we evaluate the limits for a natural log, instead of doing final minus initial, I'm going to do a division, right? Because subtracting natural logs is the same as dividing. And we like to divide in physics. Oh, thumbs up to you too. We like to do natural logs in physics because it gets rid of the units, as if you do it as a ratio. So here I have AZ is going to be equal to mu naught I over 4 pi natural log of Z. I'm going to get L over 2 plus the square root of L squared over 4 plus x squared. I switched the order over negative L over 2 plus the square root of L squared over 4 plus x squared. Now, is that simplifiable? Maybe, but let's just leave it like that. Okay, so that's important. Let's actually write that in orange so I can use a different color. AZ mu naught 4 pi natural log L over 2 plus square root L squared over 4 plus x squared, all of that over negative L over 2 plus square root of L squared over 4 plus x squared. That is what I got before, right? Just double checking. Yep. Okay. So now let's just go ahead and visualize this in Python. So let's make our wire, break it into pieces, and for each piece, instead of integrating, I'm just going to calculate JdV divided by that R divided by R. I can do that. And then add up all the pieces. Okay, so we've got a lot of work to do, and that's just for half of the whole thing, right? Because we still have to do the magnetic field. So let's jump over here to the computer in Python. I already put in some things. I got a little head start on this, right? So mu naught, I, L, and X. That's all I want. Let's go ahead and pick N. I'm going to pick N as 20. I'm going to break my wire into 20 pieces. So if that's the case, I need how big of a step size I'm going to get. Let's call it D capital S. I'm going to use DL for something else. And that's just going to be L over N. And what I'm going to do is have a starting location. It's going to keep on moving up and up until I make the whole thing. So our start is going to be vector. I'm going to do it in the y direction. 0, negative L over 2, 0. Now all I have to do is make a loop while rs.y is less than L over 2. Now this is, it's not perfect, right? Because I'm putting the piece size at the bottom of the piece. It should be in the center, but it's all going to be fine. We don't have to worry about that kind of stuff. So what I want to do is I'm just going to draw a cylinder there. Cylinder POS equals RS. Axis is going to be equal to the vector 0 ds 0, right? That's the way it's going to be pointing up. And then the radius, let's put it at L divided by 80. And now I need to move my piece. So RS equals RS plus vector 0 ds 0. And that's it. We should get a line. There's my line. And it is broken into pieces. In fact, if I go up here, just for the fun of it, and make my axis not quite long enough, 0.9 times the length, you can see the spacing right there. Now it looks like a Lego thing. I kind of like that. Okay. So one of the things we want to do is to add this. We want a list of all our pieces so that we can refer to them whenever we want. So I'm going to make a list. I'm going to call it DLS, and it's going to be empty. So DLs, right, it's plural. So down here I'm just going to say DLs equals DLs plus this thing. Now, one of the things I want to do is to add in there JdV, right? Because each piece has could have a different JdV. In this case, they're all the same. But if I made like a circle, then it would change. So I need to change that. So I'm going to go ahead and put it in here as a property of my cylinder. So I'm going to say JdV, capital V, is the vector, is I times the vector 0 ds 0. So it's in the y direction, same piece. That's my dz I had before. It says I dz, just like we said before. Okay. Let's just run it to make sure that I didn't mess anything up. Okay, no errors. Good. So we have that. Now what we need to do is get out of this. I need to make a function that calculates the vector potential wherever I want. So let's make that def a ROT. So I like to say ROT is the temporary observation location. I'm going to pass to it an observation location. I'm going to use that list of currents, and it's going to return the vector potential. So the first thing I want is a temporary vector potential. I'll call it vector 0, 0, 0, because you can add something to 0, but you can't add something to nothing. So I have to have something, I have to have 0 there to add it to. So each piece is going to make a contribution to the vector potential, and I can add it to the 0. Now I need to go through all my little pieces. So I'm going to say for dl in dls. So this goes through the list dls and calls each element dl. So now I can just use that dl to calculate dat. So the first thing I want to do is calculate r. So r is going to be the vector rot minus dl.pos, right? It's the position of the current, which is dl.pos, subtracted from the observation location, which is rot. Now I can calculate, I'll call it dA. It's just going to be mu naught divided by 4 times pi, that's my constant, times jdv, which is going to be dl.jdv, right? That's the property of that each little piece, because they could be different. And then I'm going to divide by the magnitude of r. Now I'm going to add that to the total, at plus dA, not dq, dA. And then when I'm done, I'm going to return from the function at. Let's just check it out. So ro, did I put an x up here? Yep. Let's put ro at the vector x0, 0, and then print a of ro. Let's just see if it gives me a number. It did. Okay. Now, again, it's in the z direction, the y direction in this case, which is what we said. Okay. Let's save it. What do I need to do next? Next, I need to find all of my vector potentials all over the place. So let's make another a grid of point values. I don't need to print this anymore. I'm going to call this n. I've been using n is 8. And what I want to do is make an 8 by 8 by 8 grid of points where I can calculate the vector potential and display it. So that means I'm going to need a vector ds. So this is going to be L by L, just like the length of the wire, which you could change. So ds is going to be L divided by nn. That's why I use the lowercase ds now. Okay. So I'm going to start in the corner and just move through the grid. So let's say r start is going to be vector negative L over 2 plus ds over 2, right? So that's why I'm right in the center. You don't have to do that. Negative L over 2 plus ds over 2. Negative L over 2. Yes, you do have to say it each time you write it. Plus ds over 2. It is required if you take that class. Now I can do a triple loop. So while rs.z is less than L over 2, while rs.y is less than L over 2, while rs.x is less than L over 2. Now, at the beginning of each loop up here, I need to reset my y. So rs.y is equal to negative L over negative I don't know why I was doing that. I was thinking of something else. Plus ds over 2. And then here I need to reset my x variable. rs.x is negative L over 2 plus ds over 2, right? Otherwise, it won't redo that loop. And then down here, what I'm going to do is let's just put a sphere there. So sphere, position is rs, radius is going to be, let's say rs over, not rs, L over 50. I don't know how big it'd be. It doesn't really matter. And now I'm going to move my rs value. So rs is going to be rs. I need to move it in the x direction. Plus vector ds0, 0. And when I'm done with that, I need to move it in the y direction. So rs equals rs plus vector 0 ds0. And then I need to move it in the z direction. rs equals rs plus vector, vector 0, 0 ds. Let's just see if it works. They should just be dots everywhere. Okay, there's my dots. Looks cool. Okay, now I want to replace those dots with an arrow representing the vector potential. So what I'm going to do up here is I want to have let's call this A scale equals 1. So I want to scale the arrows, right, because I don't want them to be too big. So let's just set it at 1 and we can try to put it wherever we want it to be. I'm going to comment out this. I don't want the spheres anymore. Instead, I'm just going to put an arrow there. The position is going to be RS. The axis is going to be equal to A scale times A of RS. So I'm going to give it that observation location, and it's going to return the vector value of the vector potential. And let's put the color at yellow. And that's it. There we go. Actually, that scale worked. So here's two really important things. I want it a little bit bigger. Let's make it a little bit bigger. A scale is 1. Let's just try 2. Is that too big? That's good. So you'll see that the vector potential, this is really important. The vector potential is in the same direction as the current in this case. And it does get smaller as you get further away. So those are smaller. So that's pretty cool. So the current's coming this way, and the vector potential is going the same way. So it's kind of like the electric field, but it's really more like the electric potential, but it's a vector. And so we can just look at that for a little bit. Okay. Now let's go back to the board. I know this video is long, but I told you I was going to give you a double high five. And I want to take our result for the vector potential and calculate the magnetic field, and then we'll come over here and do it numerically. Okay, so let's put that right there and go back to the board. Hello, board. Here we are. Okay. So I have here an expression for the z component of the magnetic field at that location. We're only going to find the magnetic field at that location just to make things easier. But you could easily see that you could easily expand this to be anywhere. So how do we find the magnetic field from the magnetic potential? Well, we take the curl. So we have to review the curl real quick. So in Cartesian coordinates, the del operator looks like this. It's a vector, partial with respect to x, partial with respect to y, partial with respect to z. So if I take the curl, and remember, my A vector is 0, 0, AZ. So we're going to use that already. So to take the curl is we're going to use the cross product with the operator. Now, that means that we can use the determinant definition of the cross product. So I'm going to say del cross A is going to be the determinant x hat, y hat, z hat. Now I'm going to put my operator right here, the partial with respect to x, the partial with respect to y, the partial with respect to z. Now I'm going to put my components of my A vector. In this case, it's 0, 0, AZ. So if I take that cross product, let's expand about the x-axis, like that, and I get oh yeah, right. I was like, it's not 0. It is 0. So I get the partial of AZ with respect to y. So here's my AZ function. What happens as I change y? Nothing, because there's no y in that function. So that is 0. And then the partial of 0 with respect to z is 0. Now I'll expand about this. Now in this case, we go backwards, right? So I go the partial of 0 with respect to z, 0. And here I get the negative the partial of AZ with respect to x. So I'm going to have to do that partial derivative. And then I expand about this, and I get 0, 0. So this says that the magnetic field in this case is going to be in the negative y direction. Let's just check, right? If my current is in this direction, and I know I can wrap it around, so if that's the x, then, and that's x cross y is z, so y would be into the, oh wait, that's going to give me, I said negative. Well, maybe I get another, maybe we get another negative. Okay. But it should be in the y direction, plus or minus, and that's fine. So we got to take the derivative of this with respect to x. So we don't have to worry about, that's the only thing in there is x, right? So to take, so let's put that up here. Let's put it down here. BZ, BY is negative the partial of AZ with respect to x. That's tiny down there. You can maybe see it. Let's put it up here. BZ negative the partial of A by AZ with respect to x. Okay, so let's take that. I'm going to write this as the sum of two terms, just to make it a little bit easier. So AZ is mu naught I over 4 pi, and then I have natural log of L over 2 plus the square root of x squared plus L squared over 4. I wrote that backwards. I don't even know why. And then I have minus natural log of negative L over 2 plus the square root of x squared plus L squared over 4. Whew. So remember, the derivative of natural log is 1 over, the natural log of u is 1 over u, but then we have to take the derivative of u. So if I take the partial of this, so I'm going to say by is, I'm going to put the negative mu naught I over 4 pi. So the derivative of this is going to be 1 over that. So 1 over L over 2 plus the square root of x squared plus L squared over 4. And then I have to take the derivative of this, so that's 0. But the derivative of this is going to be, this is x squared plus L over squared over 4 to the 1/2. So I'm going to get to the negative 1/2, because you reduce it by a power, and then I'm going to get a 1/2. And then I have to take the derivative of the inside, and I get 2x. And so I'm going to get this times the square root of x squared plus L squared over 4. Now the other term is very similar, but different. So I'm also going to get, I have a minus. I'll put the minus right there. I have this term up here is going to give me, again, just an x, right? Because I'm going to get the 1/2. On the bottom, this is separated, minus x over. I'm going to get negative L over 2 plus the square root of x squared plus L squared over 4. And then I'm going to get, again, all of that multiplied by the square root of x squared plus L squared over 4. It's a mess. Okay. I might make a mistake here. I can factor out that x. I can also factor out this term, and I'm not sure that I want to do that, but I'm going to do it anyway. So by is negative mu naught I x over 4 pi. Let's just do it. 1 over the square root of x squared plus L squared over 4 times. Now right here, I have an L over 2 plus that, and then minus L over 2 plus that. I want to get a common denominator. So I'm going to multiply this by that and that by this. And so this one I'm going to get negative L over 2 plus the square root of x squared plus L squared over 4. All of that over, now I'm going to get L times negative L over 2 is going to be negative L squared over 4. And then I'm going to get no cross term because it's a plus and minus. And then I'm going to get this times that, which is just going to be plus x squared plus L squared over 4. So something nice happens there. Okay. And then this one is going to be very similar. Negative x. I'm going to cross, then I have to, and x is gone, I factor that out. I'm going to get L over 2 plus the square root of x squared plus L squared over 4. All of that over, are you getting tired? I'm getting tired. Over, again, I'm going to get minus L squared over 4 plus x squared plus L squared over 4. So right here, cancel, 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 cancel. That's nice. So the x squared I can actually pull up front. So I get negative mu naught I. X divided by x squared is going to be 4 pi x. And then I have negative, well, look at this. Now I can just add these. I get negative L over 2 minus L over 2 is going to be minus L. And then I have this minus that, which cancels. I think that's it. I think I might have made a mistake too, but I mean, look, we're 30 minutes in and I want to get to the numerical part. So, I mean, I know the answer because I did it before. But let's just leave it like that. So I'm just going to put that over here. I feel like it's not completely right. Mu naught I L over 4 pi x. I feel like there should be a square root in there somewhere, but that's fine. Okay, so now what we're going to do is to do this. I want to take the curl numerically. So how do you do that? Well, let's just write out the curl in full glory. It's a mess, right? So I have B del cross A. But now I don't know anything about A. Let's assume I don't know anything. So I can say B is going to be equal to the determinant of x hat, y hat, z hat. And then I'm going to put my partials here. Partial with respect to x, partial with respect to y, partial with respect to z. And then I can put my A, ax, ay, az. So if I do this cross product, and we are going to do it, it's going to be a mess, so I'm going to put as much room as I can. So my x component is going to be the partial of az with respect to y minus the partial of ay with respect to z. Now my y component, I'm going to go this way, the partial of ax with respect to z minus the partial of az with respect to x. And then finally z, I get the partial of az, no I don't, ay, with respect to x minus the partial of ax with respect to y. Now, how do I do with these partial derivatives in Python? That's the question. Imagine that I had some function, let's say this is just ax, and it changes with both y or whatever, and it looks like this. Well, if I want to find the partial derivative at that point, what I can do is to move forward a little step, ds, move back a little step, ds, and then find those values, and then find the slope. So we're going to just use the normal definition of a derivative. So I'm going to say the partial, I'm going to say delta ax, delta, let's say delta y. Let's write it out. Delta ax, delta y. It means I'm changing the x value with respect to y. Now, I'm going to have my vector a, right? I'm going to have a function a that I can find anything. I want the x component of that. So this is going to be equal to ax of y plus delta y minus ax of y minus delta y all over 2 delta y, right? Because I went forward delta y and back delta y. So that's what I'm going to do. I need to do that there, and return a vector. I've already put that code into the computer because I know I made a mistake. So let's just go ahead and implement this thing in Python. And then we'll be done. So here we are. So let me show you surprise down here. And I even copied it from another code that I had. See, look at that. I'm going to copy this. I'll tell you what it is. Let me put it up here. And because there is a little bit of cheat. So here I have the a function. So I'm going to put right here the curl. So I used RR instead of ROT. So this is the curl function. The ds in this case is how far you're going to move back and forth. I just picked 0, 0, 1. It doesn't really matter. And then I need to pick the vector. How far do you move in the x direction? How far do you move in the y direction? How far do you move in the z direction? Those are vectors, right? So this CFX is my temporary component in the x direction. And so this is the x component of that result. So here you see a of rr plus dy dot z. So a returns a vector, so if dot z is just the z component of that, minus a of rr minus dy dot z, and then I divide by 2 ds. So all the ds's are the same. I don't have to find the magnitude of that. Okay, but I do need this dy as a vector because I need to give a vector. So I need my observation location plus a little shift. And then I do the same, then I do the opposite over here for the second part. So that's just one partial derivative right there. And then I return x component, y component, z component. That's it. Okay, so the magnitude, the magnetic field is just the curl. So that means that we can go down here and I can make another arrow. So I'm going to make another scale, let's say B scale, because I don't know how big they're going to be. And down here, I'm going to put arrow POS equals RS. I'm going to draw 2 arrows at each location, one for the vector potential, one for the magnetic field. So the axis of the second one is going to be equal to B scale times the curl of A. So I'm just going to say curl of A at RS. That's it. And then let's see, that goes with that, and let's make the color equals color dot magenta, and let's see if it runs. It didn't. Oh, it did. Okay, so it ran. My B scale must be too small, so let's make it 10. What did I put before? So I'm guessing, I put 0.7. Huh. Oh, maybe I put A scale is 2. Okay, I'm going to switch encodes, and I'll fix it because I don't want to waste time fixing it. This is already long enough. Okay, so here's the same idea. And I'm not sure what's wrong. I'll figure it out. But you know I'm not really good at these impromptu situations. So there we go. So the magenta is my magnetic field. And you'll notice it's at right angles to the vector potential. And it's in the right direction. If I put my thumb in the direction of the current, the magnetic field goes in the right direction. It gets smaller as you get further away. So we already knew the magnetic field due to this wire, right? This is just practice. So there you go. Taking the curl of that. And so this curl at that each individual point is not based on the next arrow over. I can calculate the vector potential anywhere, right? I'm just displaying at those locations. So there you go. I think this picture is, if you want to understand vector potential, you need this picture, right? Because it kind of gives you an idea of the relationship between those two. And without that, it's just so abstract, it doesn't really make sense. But this method, if you want to change to like a loop of current, all you have to do is change your IDLs and it should still work. So, and we will do that, of course, but we're starting off with an infinitely long wire. Not infinitely, I'm sorry, I take that back. If you use an infinitely long wire, you can't get the vector potential with that gauge. So that's why we do this long wire. Okay, wow, good job. I told you I'd give you a double high five. Here it goes, double high five. Well, I missed it. Let's see, double high five. Good job. Okay, good job, everyone. I'll put the code down below, link to the whole playlist down below. If you have any questions, put the comment down there. If you're questioning this and you made it to the end of the video and you're questioning and it's like 3 years later, it may take me a while to reply because I have to like rewatch the video. I can't remember. So if you want a quick reply, comment quickly. Okay, and if not, just hope for the best. And I'll talk to you later. That's it. Bye.